Many of the early thoughts about thinking about how would you possibly put this stuff together and how to really think about it, really the physics mindset of this, the physics mindset that you'll actually see, has there were things that I started thinking about when I would have been sitting, well, if we were in a non-COVID space, sitting where you were. And in fact, I actually asked one or two of these questions, early versions of it, when I actually was a student, like, oh, I wonder how this would work in circuits. And Steve was patient with me and said, okay, sure, we'll see how this goes. And I'll bring up some of those things as we go along. But it's kind of cool, it's concepts. And I'll review a couple things I did talk about last time as well. And again, if there are questions anytime, by all means, jump in, all right? So just as a quick sound check, you're all with me, right? People are with me?
Yes.
Okay.
You're clearly, loud and clear.
Okay. Cool. So last time we talked about all the cool things around neurons. And we talked about that in the end, for most neurons, this is all going to be related to looking at the membrane biophysics. And at this point, I'm sure looking at this again, people are thinking, okay, I understand. I see there's bilipid membranes. We have these channels of things that allowing ions to flow through. And we can kind of talk about how those dynamics would play out. And I'm sure at some point, everyone's gone, okay, yep, that makes sense. And the reason we care a lot is that these channels or single channels isn't just like, a little spherical block, but it's like, an entire dendritic, huge infrastructure. And this is like one piece of a device all the way through. And thinking about it just kind of harkens back to the question of, how much opportunity there is in all the computation, how amazing that what the nervous system is actually doing. Now I'm going to really spend time today focused on the Hodgkin-Huxley kind of equivalent, but we could go much wider in these discussions. And I want to kind of step back and start from the Hodgkin-Huxley kind of structure. And my guess is that these are things that are familiar to you in one form or another from your previous lectures. If they're not familiar to you, you can still tell me, even though I'm sure Steve will be like, wait, you're supposed to know all this. But I want you to kind of think about it from a standpoint of where Hodgkin and Huxley were doing things in the early 50s. And to get a perspective of that, remember that, in 1950 to 1954, which is when a lot of Hodgkin-Huxley's work was done, this would have been, only a couple years after the invention of the transistor. The very first, we call it invention, but it was really an experiment they were trying to look at. Technically, the first patent on the transistor was in 1931, but it was the first experimental demonstration. It was the first case where people were starting to talk about this, and there was sort of things starting to happen. But what you found is that, that Hodgkin and Huxley would have had very little knowledge of anything in terms of transistors and transistor physics. They might have had some new piece of equipment that had a transistor in it, maybe in their lab, but probably even then it wouldn't have connected. And so you have to ask and so even though we understand a lot about device physics, particularly if you come from a double E background, you're like, oh, well, there's lots of things I could imagine. When they were putting together their model, there was only certain tools they had to sort of think about in terms of how they put this together. They certainly understood about resistors, and they knew that there were voltage-dependent resistors. And so they understood there was kind of a Nernst potential. There was some early work on understanding some of those physics and transport. But they kind of like, okay, let's talk about there being a voltage source, which is a Nernst potential, sodium, potassium Nernst potential. I'll use EK and ENA in those cases. There would be some resistor. And then I would imagine, well, the membrane voltage has some effect on those conductances. And you're like, all right, that's great. The other thing people would have known is they're like, well, it's a chemical system, so I would have known something about rate equations, right? And you go, well, that's a rate equation there. And so almost everything there gets modeled by rate equations, and you're like, yay, great. And you think, well, this is a nice linear equation, and these are nice linear circuits, so everything is really easy, right? No problem. Until you realize that these conductances are related to functions of those rate equation variables. I'm sure you've seen the n to the fourth and the m cubed h questions, which were entirely empirical and still to this day are really empirical kind of constructs. There's some arguments about molecule things, but that's stretching it. And I'll explain more why I mean that. But then there's all the alpha and beta terms, and if you've seen the equations, the entire set of equations, if I did the sodium and potassium channels, which you probably looked at, they take a page. There's a huge number of equations all the way through. And one of the things you notice, by the way, for those of you who looked at, is there's a lot of exponentials, right? In fact, the alpha and beta terms have a lot of exponentials or tangents or other things in their formulation. And that's sort of what fell out of how Hodgkin-Huxley sort of took their data and said, hey, how do we put this together? Okay. So I'm guessing at this point, this is kind of review, but from a slightly different angle. Okay. And so then you could imagine saying I put multiple channels together, and I still can put in a capacitance because there is a membrane capacitance, and I can then talk about it. And they could also talk about either leak channels, basically channels that don't have any modulation based on the membrane voltage. But this is kind of like the model you would have been used to seeing. And I'm sure most of you are nodding going, yeah, I've seen this over the last 2 weeks. I got that right for being 2 weeks, right, Steve?
Yeah, right. And the exponentials are interesting because I think the Hodgkin-Huxley, I don't know if they were just thinking what kind of functions give those
Right.
some of those forms, and so it made
Right.
sense. Yeah, but you're
They
right.
weren't
It could be many different ways you could do it, but that would
Right.
seem yeah.
That seemed like the interesting thing. And what's interesting in the end is that they weren't aware of as much of the devices that you could argue that some of the exponentials might have come out because they might have been thinking about it in terms of those terms, because if I look in chemistry, there are some rate reaction variables that are based on some exponential terms. So maybe I could think that they're thinking, well, maybe that's a good attempt, and that's maybe where they came from.
Yeah, we were looking at the paper. I maybe saw it in the lecture. We were looking at the
one. Mm-hmm.
Yeah, and it is surprising that they put down these linear equations to because they're thinking of permissive and non-permissive states of the channel. So they were thinking channels. They didn't say the word channels, but they were talking about these different states. And so they felt that, I think they said, what was it? I can't remember which one I said. It was Huxley. One of them pushed this idea of modeling it this way.
Yeah, and there certainly was something to the modeling. And again, I look at how they put their modeling together. And for being the early 50s, it was pretty incredible. They got where they did. They got something that was so predictive as they did. It's incredible.
Yeah. It was...
And so I think that I have a huge amount of respect for it, even though we can look at it now through a different lens and go, yeah, but there's different things we can see. And that different lens is a lot of what I'm going to talk about. And how do we maybe now rethink that, given the fact that we've had 70 years of semiconductor development since then. We know a few more things. So all right, so here's how we start thinking about circuit models for channels. And and I somehow had animation I didn't intend on there, but that's okay. So the thing that we start finding when we start doing circuits is that we know that from those models, there's a lot of exponentials, where it turns out that transistors have an exponential current voltage relationship. And in fact, if I want to get current voltage relationships that even give me things that look like hyperbolic tangents, that look like Fermi functions, that look like these kinds of structures, it's not particularly challenging to come up with them. To come up with them in the right sort of maybe current voltage relationship I want, I may have to think a little bit. There's a classic circuit that we call as a differential pair. So we use the lower transistor as a current source. And these two transistors basically split the current. So basically, depending on the voltage input, I kind of can split the current between one leg or the other. There's also ways that I can take this, and actually I would use a differential pair in the structure, that I can actually do things where I can build on-chip conductances, first order low pass filters, where I just take a very simple, what is transconductance amplifier is how we would talk about this, where it's the difference of the two voltages results in a current out. if you've done op amps, you're thinking, well, that looks like an op amp symbol, and there is a crossover there. But I have sort of a bias that allows me to like tune what a bias current is, or effectively my time constant. And I have a capacitance that I, again, like I would have in the neural structure. So this is kind of where the state of the art of, or this is where people started thinking about this, when people started saying, well, I wonder what circuit models would look like. Because there's these active nonlinear channels, neuron spike, that's really cool. We want to get, neuron looking spikes, right? Things that would follow along Hodgkin-Huxley dynamics of a form. Okay, so that's kind of where that, so if you were looking at things in say 1990, or let's say 1981, if you happen to have been a student in Steve's class 29 years ago, this might have been things that people would have talked about. And so it turned out that probably what is one of the early works in the neuromorphic community sort of came out at the end of 1991, which was came by Misha Malawald and Rodney Douglas. Misha Malawald was a PhD student at Caltech. She was just about to finish up her PhD at this point. Eventually would go to which was it, Oxford, because Rodney Douglas was a professor at Oxford at that time. Eventually they would all end up in Zurich. There's a long, interesting set of story about this. And in fact, a number of things written down. There's actually a really interesting book on the history of the neuromorphic space from a particular point of view, which is called The Silicon Eye. Very interesting sort of work. Most of her work was not related to sort of neural modeling as a PhD student, but it was something she was interested in and would eventually become more things that she would do later on. So she ended up sort of taking blocks like these and said, how do I find a way to take blocks like these to kind of implement some of the Hodgkin-Huxley equations? December 1991 in Nature, sort of very famous, it was on the cover of Nature, very well there. This became the foundational work for like a whole bunch of other things. The issue that people end up finding though is that the number of transistors you had was significant. It didn't actually implement the whole Hodgkin-Huxley, but it did get you quite a ways in. It didn't do M cubed H, it did M minus H. The N was just N, but put some other nonlinearities, but actually had interesting spikes. And so you could kind of tweak it. And other people then, doubled up the amount of work and made that, made things look a little bit better. You could make it work. The number of transistors you would have would be, maybe 100 transistors for her case. The number of biases would be high. There eventually became a term in the neuromorphic community around this kind of work, because you put 4 neurons together and it would be a box that'll be about this big, right? This big, where there'd be pots all the way around it, potentiometers that you would tune by screwdrivers all the way around it. And so there became sort of the term people would be asking is, were people pot smokers? Because everyone had all their pots and be doing that. And there was a bit of a reggae cultural sense in this, so it was all the more fun. And so people would talk about these things, and it was very interesting. And so this was basically just trying to implement an approximation of these Hodgkin-Huxley equations. It does make you ask the question about how do you talk about modeling the physics? And that sort of became a different idea and different focus in these directions.
Wait, when you say modeling the physics, you mean the biophysics?
Yeah, sort of, can you model the biophysics with more of the transistor physics directly? Can you
Okay,
kind of look at how you would put that together?
Okay.
And it's an interesting question because Carver always talked about it in those terms. And you can see it in his original sort of analog VLSI book. And then everyone would make those terms, and you even see a lot of this even today. They'd make those terms and then immediately make a turn and never come back to that point again. And so it was kind of like something that was said but never kind of pushed anything further than that. And so from where I come from this, again, part of my roots was at Arizona State, good device physics background. I love the device physics stuff. Always part of my perspective was thinking the device physics were a key part of this conversation. And so that was important. I will say honestly that I do remember when this paper came out in Nature in the end of December, because I remember thinking much more from a trying to think about how to do a physics-based approaches. It was early on that day. And I remember looking at this going, oh, a little deflated. It's like, okay, let's see where this goes. But, story keeps continuing, and it's an interesting discussion there. So you say, well, how do I start thinking about the physics side of this? Well, I want to come back to something I talked about last time about, I started talking about biological and transistor channels, and just kind of review this. Now, remember when we talk about a biological channel, we're talking about that we'll have, you have your membrane, there's these pieces, and inside means inside the bilipid membrane, and the two regions outside of it. Obviously, I can have ions there. If I have no channel in here, this is an incredibly good insulator, incredibly good capacitor in this aqueous solution. If I put a channel in there, it does allow sort of the semi-permeable membrane concept that goes on, and there's some equilibrium and some voltage that's created. One way we talk about this is we often talk about this in terms of a p-n junction device, where I have a piece of n-type material and p-type material, and hypothetically I think of putting them together. But what it means is I'm going to have basically positive charges, which are absence of electrons, and electrons as my two carrier particles, and then I look at how they interact. And there will be a very similar sort of dynamic as this sort of, as I might get across a channel, as I would get across a semi-permeable membrane, which is why a barrier forms, because you kind of look at the concentration difference on one side to the other, and that kind of sets up sort of a voltage difference to kind of balance the drift and the diffusion currents. And by the way, this is true whether this is a single barrier or multiple barriers in the process. You integrate from one edge to the other in terms of how you approach it. But what's really interesting with this device is if you actually were to apply a voltage between the two sides, between one terminal and the other, and then look at the resulting current, I actually get an exponentially increasing current in the forward bias regime. Because what that's going to mean is I'm going to take this barrier and basically make it smaller and smaller. So it means I get an exponential more electrons across. Remember we talked about carriers, whether they're electrons, whether they're holes, whether they're concentration of sodium ions, potassium ions, and so forth. All things of this sort have an exponential distribution that they exponentially decrease the probability of finding them at higher and higher energies. And that's what's necessary to get across any sort of barrier. And we could talk about, ions or bosons, electrons or fermions, and the tails but the tails are all exponential. Okay. So that may be more physics than you wanted to know, but that's kind of a rough thing to think about it. But then when I look at it from a transistor, it's kind of, a double barrier here, but it's basically, I have a source and a drain, and I basically have a voltage controlled barrier. And this is really kind of a neat concept because I have a voltage control barrier here. I'm going to get sort of exponential number of carriers going over one barrier, exponentially related to the barrier height. I'm getting another one that's exponentially related to the barrier height. And then I get diffusion in the intermediate region in between. And then what changes this intermediate barrier, this region here, which by the way, we call this region a channel, interestingly enough, and we talk about what modulates this channel as a gate. For those of you who've been staring at biological channels, you're thinking, wait a minute, those are all the similar terms. I'm like, yeah, interesting enough. Not that anyone initially put them together. And if I were to take the gate voltage and sweep it, or change it, and then have some voltage difference between these two terminals, a source and a drain, I get a nice exponential response that I can then curve fit, and it follows a nice exponential. So one of the things that you notice is that exponentials show up naturally all over the place in the physics. And that's really important to kind of notice because that is relevant to what we're, it's relevant to a lot of things we've even seen, even how Hodgkin-Huxley put their modeling together. We also see that, we want to ask questions of, well, how does transport go through a barrier in terms of barriers on different sides? And we want to kind of think about these questions, okay? Because in a biological channel, what are we actually seeing here when we actually look at this carefully? Okay. There's a lot of physics, but hopefully again, having seen it at least one more time is probably helpful. If it's too much, by the way, I'm serious. If anyone has any questions, please ask.
I have a question.
Yeah.
So with the p-n junction, what can you explain like what the EC, EF, and EV are?
Absolutely, thank you. As I'm eating a snack because it's dinner time. No. EC and EV, those are conduction band and valence band. EF is a Fermi level, which then when you actually apply voltage is called a quasi-Fermi level. And you might go, what are those things? And what you find as you talk about in silicon is that there's a valence band and a conduction band. And what it turns out is that there's a band gap between them. And what it means is that there's a region where, at least in a pure piece of material, there's no carriers that are allowed there. This comes from all sorts of solutions of Schrodinger's equation, which is quantum mechanics over certain spaces. And kind of says that, oh, look, there's a barrier there. What's really important about that is because there's a band gap, it means that I'm going to have like opportunities for a few electrons sitting up in the conduction band that are really going to be the carriers I care about. And the valence band is going to be mostly all filled, mostly all electrons filled there with a few absences of electrons. We call those holes. And those absence of electrons now are basically positive charges, which is always a little strange when people think about transport, because you think, oh, look, I want to think about electrons like marbles, and I'm like counting how the marbles move. But if you look at it closely, what we mean by electrons is really a perturbation over a sea of electrons. And a hole is a perturbation over a sea of electrons in quantum mechanics. And so it kind of works to think about them as separate particles-ish.
So like are the minority and majority carriers, they're both electrons, but the majority is like a little less negative?
Yeah, so what happens is you have a whole bunch of minority carriers and majority carriers. And what's interesting is, so what's fun here is that you talk about, in this case, electrons, which are the dots, are minority carriers on this side, and the holes are the majority on this side. It turns out because you can tell where the Fermi level is, because that's kind of like where the probability is a half. What happens is is like, oh, well, that means if it's half here, that means I have a lot more holes than electrons. Similarly, the Fermi levels near the conduction band is sort of my halfway point. So it means that I've got a lot more electrons up here than I've got holes down here. So that actually makes this kind of interesting in terms of how you look at things. And what's interesting is it has a lot to do with how these how these structures are, in terms of how I set up, basically this being an N-type piece of material which has a lot of electrons, and this being a P-type piece of material which has a bunch of holes in it. I've actually sort of put in my silicon a few extra ions in here and I put a few extra ions on this side such that this one gives me more electrons and this one gives me more positive charges. So that's kind of what you're trying to do.
Excuse me, is everybody be able to see the screen? Because mine went blank.
Oh.
What about other people?
I can still see it.
Okay, that's my problem then. Okay, I'll continue. And I'll.
It's completely possible the text network would have gone down, but.
No, I think it's on my end. Maybe it's
okay. And to be fair, the device physics, like in a transistor device physics, it's usually like a whole semester course. So I'm throwing this at you all at once. But I think there's certain couple core concepts that are important here. And the thing to realize is because of the band gap, I actually have two different kinds of carriers to work with. One positive, one negative. If you think about it in terms of the aqueous solution in a biological channel, typically for the salts, I've got multiple positive ions, sodium, potassium, calcium, and at least one negative ion, right? Chlorine. We always sometimes forget the chlorines, but they're there. And that also gives you some of the negative pieces of that. Does that help a little bit?
Yeah, that does. Thank you.
Okay, cool. And please ask questions as we go through, because, you know, that just makes it more fun. So there's a lot of interesting pieces of this sort of core device physics here. And so what you find is that both biological, that we end up getting some interesting equivalents there. Well, I want to talk about that. We talk about the exponentials there. So this is sort of a slide that'll take a couple minutes to go through. And then each of these couple will take a few minutes there. But one of the things we talk about a transistor, right? And I was showing it on the previous slide, is that I can talk about there being effectively, voltage control barrier from source to drain. And that there's a channel here and a gating phenomena. Well, if I look at a biological membrane, what am I going to see? Well, again, I see my bilayer, right, bilipid membrane that I'm looking at. And then there's this part for the channel, which of course has its own molecular structure. But if I look at it, there's going to be some sort of, this is inside structure, this is outside structure, and then looking at what's going on right through the channel itself. And if you actually ask, what does it look like going through this channel? Typical calculations for that potential from one end to the other looks something like, you might get something like this sort of structure. And different things in different pieces, but you might see something like this with a small peak in it initially. This is highly dependent on different parts, as well as also doesn't matter much because you usually shoot straight through the barrier because it's so thin. It's a tunneling phenomenon. There is kind of like some sort of variation in the barrier. Sometimes this may be a little peak or something there, depending on the molecules, and then back out. So this is what you end up getting from certain numerical simulations. So yeah, I mean, and by the way, if you want to know lots and lots of details about, about stuff like this, you usually start going, where is Hill's wonderful reference on channels, right? I'm sure Steve knows exactly what I'm talking about. If you don't, it happens to be within arm reach of me. This one. You really want to go through this in great detail. You probably don't though, but in case you do. So yeah, for the device physicist and me, it's great fun to dig into it. These are the kinds of things that you see. What's also interesting is that as you change the inside and outside potentials, these barriers will move up and down with the voltage. So if there's a voltage difference between one side of the channel, this will be at a lower potential, and this one, depending on the potentials. Further, so that you can get all of that. These sort of spiky things, when they show up, is not terribly relevant because you tunnel through them. There's a couple parameters, but this particular height also depends on where the gating potential is for that channel. There's always like a gating potential of what it looks like at the membrane, but on the inside there might be some biochemical molecule that senses what's going on this side and then modifies the channel potential accordingly. Okay. So there's something going between what you're sensing and the actual gating potential. And so this actually moves up and down with that. Interestingly enough, if I show you what the band diagram is from source to drain of the transistor, it kind of looks like this. And so at a very low level on the physics, they look very, very similar. And so it's really quite interesting. And then you might go, okay, yeah, that's really cool, but I thought I heard about these like biochannel, people talk about measurement from biochannels, from single channels, you start to say, oh, look, I've got these telegraph signals. So that must be the most important part of this whole conversation, right? Well, I would argue no. And I think there's some good physics behind that conversation. It is relevant. It is relevant with any chemical system. You're going to get these conformational changes. So if you get to go deep in your orgochem, you get to find out that these things, shift in stage and they go back and forth. And this is always what happens with sort of larger organic molecules. And these are certainly organic molecules. Interestingly enough, depending on where the gate potential is, will also depend on how fast you end up moving in certain conformational states. So that's also kind of fun in terms of just the just your your statistical dynamics or statistical mechanics of the system. So that's interesting, but and so we could always talk about, okay, maybe there's that additive noise or structure on there. But there's an interesting experiment that I find much more interesting, because often we talk about, if we have a whole population of channels, we go from telegraph signals to, nice voltage clamp experiments, right? And everyone has heard of a voltage clamp before, right? By now? Yeah, we're going to come back to that, but we'll start there. This is a voltage, like we might see a voltage clamp measurement. Here's the thing. And so you say, okay, well, it's just, single channel to many channels. Well, funny thing is, if I give you a transistor that's a nice wide, say 1 micron width, right? So this is like what I imagined for a transistor. Here's the gate of that transistor. Again, imagine I take this picture and I'm looking at it from the top view. So I'm looking down at that transistor, right? From top. I would see the gate, I would see my source and drain, and I would see these little black things, which are metal contacts to all the rest of the structure. Okay. And if I looked at this, I would see nice continuous IV curves. In fact, I could generate a curve like this from a transistor. We'll get to that later, but you can probably believe me, that's probably true. Interestingly enough, if I take a transistor in this kind of a process at a really low current, like 1 picoamp of current, and make it super thin, like the thickness that I would expect from a single channel, like 1 nanometer thickness, which these days we can actually get pretty close. We start getting close to this. You can start seeing these effects, and device physicists get scared of all these things because they're like, oh wait, we're seeing like various multiple carrier shot sort of effects. At the right time scale, I can actually get this kind of measurement out of a transistor as well. And it turns out it's in the right sort of current levels that's what I would see. So it's an interesting question, because even if I had a structure and the membrane was always open, I would still be seeing likely some level of this granularity in terms of the telegraph noise on the structures. So what you end up finding is that the conformational change is interesting, but not the zeroth order property on what's on the physics of the channel. And so that turns out to be really important to kind of get a sense of what's happening there. Even if you like go through a book like this, it takes you a while till you really, because like 80% of the experiments are all channels opening up and down, and then there's 20% are on the barrier, but it turns out that those are all the things that dictate all the rest of the physics. It's pretty interesting. And so that brings me to an interesting place. So before I jump into that, does that make sense? I probably talked about at least some physics.
Yeah, I was going to ask, so I'm a little confused. So 1 transistor would be like 1 channel? Am I missing the point here?
You could eventually do that. Now, the way we approach it is if I had multiple channels, it's like I have a bunch
That's
of
what you
them
mean
in
by
parallel.
times 1,000? Is it
Yeah,
multiple?
well, if I had multiple channels, it'd be like a bunch of them in parallel. If I have a transistor, I could imagine it being a bunch of these very thin slices all in parallel. And so if I had multiple things in parallel, they kind of average over each other.
Okay.
And so the point being is that I could get things to be single transistor being equivalent to a single channel, or I could get a single transistor to be equivalent to a whole, because a single transistor might be wider, being a set of multiple channels.
Right.
And so that distinction is less important. That distinction is very fluid when you look at it from the hardware standpoint. Fluid may be an interesting, may or may not be an intentional term, but it's very much, you can kind of look at both sides of that. And you could actually talk about transistor being single channel if you wanted to go there.
So yeah, you can get down to that level. So
yeah,
I'm thinking in terms of like dendritic spines. The spine heads may not have that many channels on an individual spine head, and so they may actually look a little bit stochastic in real life, as opposed to when we do the modeling with the Hodgkin-Huxley spines, we're assuming there's a lot of channels on each individual spine, but it may not be the case.
And some of the stochasticity is just the carrier movement through it.
Yeah.
It's just the carrier movement and the grouping of carriers as they're transporting through the channel as much as anything else. And you'd see that in either situation. So the stochastic noise, What you would see on a CMOS transistor is you would get less of it. You get less stochastic noise than you would in the biological case, but you still would see it. And there's some really good connections on the physics. So just one of those things to think about.
So is channel noise distinct from thermal noise?
Yes.
And how would you know
It
that?
would be true in both cases, right? Because the channel noise the noise that you get in a typical channel, I think, is more of a 1/f spectrum noise, more than it is a thermal noise component, I believe. So it's an interesting question, right? So if you have transport noise, the typical simple transport noise will probably be thermal. The conformational change noise will likely be 1/f, I think. I'd have to check that. Interesting, and so you'd have both components. And in transistors, you have both components.
I see.
So to really get that tied down, one could probably do that without too much difficulty. So just some good stuff there. So cool. All right. Hopefully I haven't buried everybody in physics yet. So is other people with me? Okay. Ishwarya, are you with me? I hope.
Yeah.
Okay. Yay, good. At least I didn't lose the PhD student. All right, good. You know, there's a lot here, and I wanted to and I hopefully, my guess is bits and pieces have been talked about in one or two other lectures. But these are questions that show up, and people often talk about some of these various aspects. And one of the things that when you see this from the physics standpoint is that there's some very nice general aspects you can think about. And sort of simple ways to think about it, but I know there's a lot just to digest. So that's cool. It's cool if it's taken a second or two. So here's where it gets kind of fun as you go, well, wait a minute. What it basically is saying is whether I have a biological channel or I have a MOSFET, where I'm going from outside to inside, in this case, we're a transistor going from source to drain, they both relatively are equivalently modeled in a very careful physical sense between source and drain as a voltage control barrier that looks like what I would see in this transistor. And I'm talking about a transistor has a channel, the biological membrane has a channel, both of them have gating mechanisms that modulate that surface potential, that channel potential. And you think to yourself, well, that's interesting, right? And that's interesting physics. But let's say I wanted to really deal with Hodgkin and Huxley's kind of data, right? And let's say I could go back into 1950, 1952 and talk to Hodgkin and Huxley and say, hey, there are these things called subthreshold transistors, transistor behavior. And, this would be great for the kind of related to the modeling you guys are doing. And after they're kind of staring at me funny, we go, well, how would I think about those experiments? And what I might say is like, well, okay, remember that in a biological channel, that these are going to look very much just like the transistor. And if that is true in a reasonable sense, and there's a lot of grounding for that, and you've gotten a sense of that, well, what's different here? Well, I know I've got a gating potential here that sort of sets this potential, but I know that there's some piece of that sort of biological membrane that's sensing the voltage from the inside and then changing the channel potential, right? That's what's distinctive about what we call a sodium channel, or what we call a potassium channel. And again, remember, if it's a sodium channel, there still are going to be like sodium ions and some other ions coming through there too. The sodium channel doesn't mean there aren't any potassium ions and stuff. It's more sort of describing various electrical properties and the primary carriers that are moving through it. So you're like, okay, that makes sense, right? So, okay, so you think to yourself, what do I need to do to make a biological channel and the transistor sort of fit? Well, I might imagine I'm going to have a sodium, here's my Tor transistor for my sodium device. It turns out, and this is a more deeper question on the transport, but I would still need to like supply the sodium potential, the Nernst potential in here, supply the potassium potential. If you're curious, I can go into why, but we'd apply those, but we'd actually apply them at those voltages, right? Sodium potential is usually about 50 millivolts, potassium is about -75. I like to do things in factors of UT. UT is KT over Q, RT over F. 25 millivolts at room temperature. So, this is basically ENA is 2 UT and this is -3 UT. I think in UT units, there's some real reasons for thinking about that in a deeper sense. And so what you would say is like, all right, I can set this up, but what's the thing I need to figure out? Well, say for the sodium transistor, I would need to say, well, what is that sort of sense of the membrane voltage, which remember is inside. Of course, I've got capacitance, so it's inside. What is that dynamics I need to do to create that gating potential? And those are, I'm going to call sort of my sodium dynamics. I'm going to call that my sodium potential, say sodium gating voltage, VNA in this case, and figure out, okay, what should that look like? And the same thing with the potassium dynamics. I might say, well, let me look from here, work through the circuit and see what makes sense. And in fact, this was part of sort of the interesting work looked at in this case. And there's some interesting stories behind all of this. But to kind of say, well, how do we do this? But how did we think about this? And this is kind of what I want to get into in the next slide. But what I wanted, most of you you're familiar with that Hodgkin and Huxley built they had their original data, right? And we actually went and took their data and grabbed all of it, put it into, basically grabbed it all so I could get numerical values, stick it all into MATLAB. Yay, we like MATLAB. And we like a lot of things, but MATLAB was good. And then said, all right, so given these devices, right, given that the transistors are acting in a certain way, and we used two PFETs, that's what the circles mean. Their PFET is a particular type of transistor. What, for the voltage clamp experiments, what did VNA and VK need to look like? Now we could ask the question of what is the currents, right? That's the classic way of talking about a voltage clamp experiment. But what we asked is then to say, well, what would the voltages look like? What do the voltages of those things look like? Because what I really care about then is what is V membrane to VNA, what is V membrane to VK? And if I get those dynamics modeled carefully and correctly, then I've really captured sort of the behavior that's going on in that particular preparation, right? The squid axon preparation. So that's where this is going to go. And that's actually what we were kind of figuring out. Now, it's an interesting question. People might go, oh, it must have been easy to do the potassium one and then do the sodium one. Turned out it went the other way. The sodium one was actually pretty easy to figure out relative once we got caught onto it. The potassium one took some time because it took some time to kind of see it from different angles and then look at different models that other people were proposing of sodium channels, and then that eventually got us where we needed to go. So that worked out well.
So the activation and inactivation didn't.
What is that?
Activation and inactivation of sodium. That's talking about the currents, I guess, or conductances. Mm-hmm. That didn't present a problem as much as the potassium.
No, it didn't. Oh. And this is what got really interesting because the potassium took a little while to figure out what's going on, and particularly relied around. Everyone leans on the end of the fourth parameter. And it took us a while to figure out what the heck was actually going on. The sodium one was actually much easier to figure out. So let me walk you through a whole bunch of things here. I could spend a bit of time on this figure without any trouble. This is sort of the circuit we had before, right? In terms of the idea that we're trying to do with these measurements. It would turn out eventually that what we needed to get from the sodium dynamics and the potassium dynamics, these became the eventual circuits that very well fit the Hodgkin-Huxley data. When we pulled the data through from the voltage clamp getting current and pushing it back through VNA. We could invert what was going on through this transistor. We could invert what was going on through the potassium structure. So, and of course, I like making these plots like I do on both sides because these look a lot like Hodgkin-Huxley's original plots, don't they? Right, where you talk about what happens for various voltage steps on, voltage clamp steps, right, all the way through from 21 millivolts to 100 millivolts, right? In fact, if I didn't tell you and you didn't look really closely at the numbers, you'd like, oh, those must have been Hodgkin-Huxley data, right? Well,
Yes, they look very similar. Yeah, with
Yeah.
the currents going in
This
and
actually-
out. Yeah.
These were this was the transistor curves, and we put them together, you see it. And actually, when we did the original modeling, we did them with transistors that were huge because we actually could like play with stuff in discrete forms and wire them together and not have to worry about any parasitics. That's why you're asking, why are these currents in microamps? Well, that's because the transistors, for those who know these sort of structures, had a W over L's or over 1,000. And so huge, so the width versus the length, so they were really, really wide, which allowed us to get really nice behavior with sort of wiring stuff, sometimes on a breadboard to try to get everything figured out. Because when you're doing this the first time, you have no idea, right? We didn't have, configurable technology the way we do today. So which changes the discussion. So that's how we put it together. But it's kind of cool. It'll be like putting, the little sizes for the time and all of this. But things that you notice, and if I showed you the Hodgkin-Huxley data right next to it, I should have probably showed that. You should see in the sodium clamp that it looks like it, hey, look, it looks like, I get a very fast, this, by the way, this is a bandpass kind of step response for those who are double E's, which means it comes up and then falls back down. It comes up and falls. These are basically bandpass responses. What was really interesting is that as you go to larger and larger, after just a small amount of increase on the amplitude.
Wait, what's the rest? What are you stepping from?
We're stepping from rest.
Which is around what? How many millivolts?
Which would have been stepping from it would have been about minus 75 equivalent.
Oh, okay.
Yeah.
Okay.
Yeah, so that's how we would have played this. Which is actually relevant as we dig into this a little bit further. Because as you look at the steps, and if you say, let me take a look at the peak values of this, one of the things you notice is that after I get about 40 millivolts, the peak value doesn't move much at all as I keep increasing things on this side.
That's the inward current.
Yeah. Okay. And it kind of doesn't get much more, and then it kind of, and you get this band, but this is a bandpass filter step response. It turns out this circuit gives you that nice bandpass response, and every single transistor we picked in here was to try to get as close to the dynamics that Hodgkin-Huxley had in the linear part and the nonlinear part. One of the things I liked a lot out of this, though, is we start looking at the gating voltage we need, and this was our sodium gating voltages we need. So basically our VNA, which was the peak value for getting these peak kind of curves. These are the current curves, and then there's voltage curves. So there's subtle differences in the dynamics. What you ended up finding is, as I made small steps up to about 35 or so, that it was pretty much almost a linear relationship. It was pretty cool, actually. And then as I got a little bit higher, it basically started rolling off to being nearly flat. It kind of flattened out over a certain time. And then given how we set up this experiment, eventually actually, as we got closer to about 100, it started to drop down. Well, the reason it started to drop down at 100 was at that point, I'm now getting within about 25 millivolts across this channel transistor. And so across that channel. And so now that channel is now, moving more and more towards the channels almost being turned off. And so if you actually were to take a look a couple of the points further down, it rockets down to where I hit the reversal potential. Which, by the way, is the same thing that Hodgkin-Huxley saw. It was like, oh, that's exactly what they were seeing and exactly the situations we were running into. This is interesting, though, from a circuit perspective, because I look at this and I go, oh, this is an amplifier that has a soft saturation point. In other words, it sort of hits a power supply rail in a soft way. And then, obviously, then this part right here is entirely due to the transistor behavior. So it's incredibly predictive of what you would have expected. it also turned out that I could build it with just a straight bandpass amplifier with a certain gain in it, with certain utilizing the nonlinear behavior of the transistors in a certain way. By the way, this wasn't necessarily the only way this could be built. You could have imagined other ways to build this circuit. But this was a nice easy one with 3 transistors and a capacitor, and worked well and had those kinds of dynamics. We'll come back to that point a little bit later. But then on potassium, it ended up being that what we built for the original structure, and these were the potassium curves. By the way, you can always tell that you actually get some very similar things to biology, because you always get these interesting jumps initially if you look at current. Hodgkin-Huxley was very careful. They actually plotted conductance initially, but if you actually put a voltage step in on these things, there's always got to be a jump. You can actually see it in one of their curves that you actually get these early jumps, and then you get the movement on the currents. So this was actually really, really kind of cool to see. It took a little bit to figure this out, but it turned out at the end, the circuit was fairly straightforward, that we had a membrane with a capacitor coming in, which is a high pass, because this transistor already had an exponential current voltage relationship based on this terminal. So the whole point of the circuit in some respect was, if the membrane voltage moved up, I want to basically pull this voltage up to kind of slow the transistor, to slow the potassium from grabbing hold of that membrane potential, and then over time let it relax back so that way it could actually do something. It's kind of almost an inverted way of thinking about it, and it had a lot to do with which transistor we chose here. But this would be the current levels that you would actually see out of this. And so we were really, really careful on trying to model what Hodgkin-Huxley's data was actually looking like. It just scaled linearly based on we're using different currents. So you would have thought, oh, look, we just have a bigger preparation that we're actually stimulating. Okay. So it gets kind of fun at this point, and it's kind of neat to actually see all these curves at once. But what's also interesting is that, you know, with all of this dynamic, we actually match all of the voltage clamp data, and it's really still at this point, well, 1, 2, 6 transistors. You're like, huh. Well, and certainly are a lot of interesting equations you could write, but it's 6 transistors to do it. And let me just kind of summarize the mindset of what we're trying to do with this. In one case, and we sort of saw this in terms of the classical sort of circuit modeling, like we saw with Misha Malowitz stuff. So, oh, look, I've got a channel. There's a whole bunch of linearized modulation of that. That's a resistor. I try to approximate a resistor. I approximate some conductance modulation, and I build circuits to try to, you know, work all this out. Versus saying, here, why don't I actually say, well, I know this starts off being a transistor. There's a real clear connection. I need to figure out the gating potential. So then I want to take a look at how does this look? What's my reversal potential? And then build those feedback elements as a result of it. And that turned out to be very relevant, actually very predictive in a number of different places, which turned out to be kind of cool. So when you put the whole thing together, sort of taking the curve from top, you end up finding like, hey, I have this entire structure. I can see the similarity between channels and transistors as a result of that. This really interesting conversation of various different dynamics that I can use to modulate the gating potential, which then gives me nice action potentials when I'm done. You're like, oh, that's kind of cool. And we can go into the pieces of that. By the way, this is relevant, and I talked about synapses a little bit last time, but it turns out when we talk about synapses, we'll actually use the same sort of formulation and modeling to be able to, you know, to be able to model its dynamics correctly. And then the questions we ask are, what is its gating dynamics? So the same sort of question came into play here as well, to get you your nice, you know, postsynaptic potentials that you see here and so on. So yay, so we could actually use physics to kind of help us through this whole process. So now we can take a closer look at some of the pieces. But before I do that, before I dig super deep, are there questions at this point?
Any questions from the class?
I guess it also includes the Swaria too.
And I heard you talk about this a lot, so I think I'm good.
So at some point, and I know you've done it, is there's a transition to equations for the silicon equation version. And so just so, you don't have to show us how you do it, but what's the thinking behind that? Because it is as a form of logarithms and stuff like that.
So if you look at the behavior for the transistor equations, they are going to typically, these transistor equations I would use here are really difference of exponentials. I'd have one exponential minus another exponential. And so, like say this current here, INA, or INA is a good example, would be related to an exponential function of this voltage VNA and ENA. And that would be how that equation would be written. There's a capacitor here. This transistor here, IK, would be related to VMEM and VK, and the fact that then there's also EK underneath it. So there'd be exponentials on those, really VMEM and VK and EK on those terms. So that would be what that equation will look like. And so when you finish this, what you find is this would be a fourth order system. It's only a fourth order system. That's why we did with transistors in this case. It's purely a fourth order system, not a fifth. There's no parasitics in there.
There's a space clamp. Yeah, of course. Yeah.
Well, no, this is actually this is what the whole transistor, this is what the whole thing looks like. This is like the whole Hodgkin-Huxley circuit.
No, I mean, the equations, you were thinking in terms of not propagation at this point.
Right. This is just a point. This is a point.
Yeah. But that's the same number of equations as the Hodgkin-Huxley.
Yep, it absolutely is. And that's absolutely what we needed to model their data perfectly. And what I end up getting is, there's one membrane capacitance, there's one additional state variable for the potassium side, and because the sodium is a bandpass, we needed two state variables, which isn't shocking because, Hodgkin-Huxley talked about it as activation, inactivation. We would just, there's really just a high pass and a low pass part of the corners for that structure. So that part is relatively consistent, but we typically will talk about sodium channel as a bandpass channel, and we'll talk about potassium as a low pass channel. And that's typically how we would distinguish between the two of them, because that's sort of functionally what we're going to see, which is kind of interesting, right? And it's actually interesting when you look at this circuit and you talk about equations, and that's absolutely essential. But what's really fun is also, if you have a little bit of circuit background, when you look at this circuit, and Ashwarya could probably vouch for this, that there's all sorts of things intuitively that come to mind when you see the circuit. That there's a whole intuition that comes along with circuit analysis. That, for example, I know this is a bandpass filter of a certain form. This gives me another filter function of a different form, and it actually there's intuition that comes along with that helps. And that'll actually get useful, and that'll be useful in certain places. For example, having a bandpass filter here says that really what's important for eventually getting a spike and getting the destabilization of that behavior for a spike is I need to have stimulations that happen within a certain that need to affect a certain frequency range. So in other words, if something stays pretty much constant, it's not necessarily going to destabilize. And so this gives you all sorts of interesting possibilities, and again, that seems to be something you would see from the original core physics originally as well. So it's kind of interesting there.
So could you look at a circuit and somehow determine whether it's going to be so they call it type 1, type 2 type onset, or let's say a Hopf bifurcation versus a homoclinic type onset?
To some extent, yes.
You really, from just looking at the circuit?
From the circuit topology, you often can tell, yes. And that would be, and a lot of that is that you kind of have a sense of the kinds of nonlinearities you have from the circuit structure you're using. Yeah, you would be able to tell quite a bit of that right from the circuit block, which might be a little more advanced than we want to get into in this conversation, but yeah, you could do that to some extent. And of course, you can keep testing me and see if it works sometime.
Yeah.
So one of the things that we also like to show is here's one example spike. We created a lot of different spikes. You can tell this is experimental data because you can see the noise on it, on the edges.
It's not
and
that
stuff.
much noise.
No, it's not bad, but it's a little bit of noise. You can see that. This was actually the spike behavior as it came up and came down. This was a pretty nicely tuned spike. Had a little interesting recovery. I think this was a single spike, and we just had a single fire spike on this one. So you can actually get cases where it fires once and stops. You can get it where it repetitively fires.
How come there's so much little noise compared to the linear model we were looking at?
Not sure. I think we'd have to go through that more carefully.
Okay.
But yeah, this was, you can kind of see the time scale, around a millisecond for the whole spike behavior, spike plus refractory period. These things were all shiftable depending on what we did. One of the things I remember Ethan was so happy about when he did this is you could actually show, here's how the potassium current behaved. Again, this is all aligned to the same time axis, how the potassium current behaved, and then how the sodium current behaved. And he was really happy with the fact that there's this interesting notch here that you get, but the sodium current is moving really fast and it comes back down. But you have this slight little peak here, which is due to sort of how the potassium, because of how the get to the peak voltage approaching ENA, the potassium current starts shifting you the other way and out you go. And so very much replicates sort of the modeling that you would expect on the different pieces of currents. So tried really hard to do that. The cool part, by the way, the circuit people all looked at this and went, wow, this is cool. You could get away with this in 6 transistors. If you looked at Misha Malawald's structure, it was about 100. So first things ever, when the first time we presented this, which was in Telluride on a Saturday morning, the first talk out in the morning, and 9 in the morning on the second week. So we only had, maybe half the people would show up that day. But the people who, and they're like, oh, they're all looking at me like, oh, she's going to talk about, this topic or that topic. And apparently we've been working on this for like 2 weeks up at Telluride to finish it out and get all the structures. And we kind of came, Ken's like, hey, let me show you all this data. And everyone was just like, oh, we had no idea this was even possible. So it was really cool to kind of start talking through that in that community. There's stories around that, which is great. So then you can get into all sorts of more additional data on these spikes. And this again comes out of, the paper Ethan and I did, which doesn't feel like that long ago, but I'm looking at the year and it's a long time ago. But then what you can imagine doing is you get clear, near threshold. And again, these are really wide transistors. So we're gonna have high currents here. And actually, yeah.
That's from the simulator?
No, this is experiment.
God, there's just no noise on that whatsoever.
I think these are, well, hold on, let me check. No, this was, I'll tell you why I know that this was actually simulation that I picked. We actually had experimental data that was very close to this, but I'll tell you why I know this was experiment, or this was simulation. Because getting this spike to behave at at the 2 milliamp level, because threshold current was just short of 2 milliamps. So you get current. So this is sitting right at the edge, just before you, just soon after you cross the boundary. This worked out really well. Nice repeated spikes all the way through. When I went up to higher current, you definitely see all these edges. And then we could end up, as you go to higher current, you can see the bottom part starts to push up on you as you get. It's not 2 milliamps. That was almost where we crossed 20. No, that's a slight mistake. Sorry about that. About 20. So you can see it sort of pushes up, and then you can also see that you get a nice FI curve, which looks like that kind of square root curve, and then it stopped.
That's very much the Hodgkin-Huxley type dynamics, right?
Yep. And so it went all the way up there and it stopped. And that was very cool. And you get exactly the square rootish kind of coming out of the bifurcation and drop and all of that.
And the students should see that the amplitude is decreasing and it's probably going towards the supercritical Hoff bifurcation.
You mean over
towards
in this area?
excitation block? Yeah.
Yeah. I mean, because this part right here is your classical square root out of the bifurcation. And then you start to see this and then it breaks. And it usually breaks, so you can see this thing sort of collapses right here. These two collapse and then it just crunches.
Well, it doesn't go into a sinusoid?
No, it's constant. When it stops, it stops.
Oh, yeah, it goes to a steady state.
Yeah, it's a steady state.
But right before that, the
Yeah,
oscillations should look sinusoidal.
Well, I mean, take a look at this one. It's not too bad. This
No,
is
it
just
still
before
has a
break.
spiking-like behavior. You still see the fast and slow.
Yeah. But you still get, and as you get close to it, it's close to that, and then it's collapsed, and then it basically becomes DC. So it never quite becomes perfectly sinusoidal, but you wouldn't expect it to ever get quite sinusoidal given the
But
structure.
you would in the Hodgkin-Huxley model.
Yeah, in the
becomes-
model, maybe. I don't think in the physics you'd see that quite the same way.
So that means some sort of
It's
it means
the
it's
nonlinearities are not
subcritical.
perfectly balanced. Although
means
it'd be
it's-
interesting if we got right to the edge of that bifurcation, it might look sinusoidal, because I guess in theory you'd always be sinusoidal right at a critical
That's right.
point. So it probably does. We just probably never got brave enough to get.
That's why it'd be good to have the equations.
Yeah, we never got
See
brave
what it's
enough to
doing.
get close.
Yeah.
By the way, the reason I know these are one or two other experiments. I'll say we actually did the case of like, let me take the membrane and like hyperpolarize it hard, and then release, and then it definitely spiked, and that was cool. The other thing is, this was the other classic experiment where we put the current. In this case, I think we put it right at about 1.7 milliamps, and just left it there. People say, "Oh, I'll do this with additive noise." We didn't add any noise. It was just the noise that showed up.
Right.
And this was our output. This is the spike. Notice this is in seconds. This is the spikes waveforms that you would get out of it. But you definitely could see the behavior based on the noise. So you could definitely see that even if you were sub threshold of the spiking, it still fired, and it fired because of the noise and where the noise was. We went back and checked where the noise was, and actually all of those spikes primarily happened when you had sort of faster jumps up in the noise. And that's what was actually giving you some of that result. That's why, by the way, I knew that this is theoretical, because we actually were looking at these questions a lot because we wanted to do FI curves experimentally. Well, we could do FI curves in this region pretty well, right? Say from about here to about here fairly well. But if I wanted to get down lower into this region, it was nearly impossible to get a really good FI curve, because I always kept going, oh, it's just flattening out. It's just flattening out. Well, that's not because the FI curve wasn't flattened, was behaving differently. It was because all the noise that was naturally in the system would cause it to spike. And then we started talking to people in the neuroscience who measure from real neurons and say, oh yeah, we can't ever get FI curves all the way at the bottom either, because it's some of the same noise problems. So we're like, yay, more predictive stuff. That was cool. So we had a lot of fun with that. But this kind of gives a sense of that we really had sort of the core dynamics in this, at least kind of initially demonstrated, and like, oh, this is good stuff. So that's kind of where we're going with that. So there's a whole bunch of pieces there.
Quick question.
Go ahead.
I had a quick question. So if you pulse the current, so this is like a constant current, right? If you pulse,
no, so these are always step. So if I have a current, it would be a step up. So to get the spike frequency, there's always a step in it, and this was always though for, as you can tell from the curve, it was always from cases of making a step and getting repeating firing. Because you can get to a place lower occurrence where you can get an action potential, but not multiple action potentials.
Yeah, so what I was wondering is, if you pulsed the current, does that alter the spike frequency?
So if you sort of pulse up and pulse down?
Yeah, it's like, you mentioned that like if it's low, if the current's low enough, you only get one action potential.
Yeah. If it's low enough, you can get one action potential. If it was high enough, but at a place where you get repetitive firing, you get repetitive firing until you pulled the current down, and then it would stop. But the frequency you would get would be more or less the same.
Yeah, I was just wondering, it's like if you get a single action potential when you step the current up, and then you step the current down, would you get another action potential when you stepped up again? If it's low enough, if the current is.
Yeah. If you stepped it up again, you would definitely get another action potential.
Is that frequency kind of, would that always be, I guess, lower? I'm just kind of confused as like how the frequency. rises out of the
If
current?
it's a single action potential, I mean, there's not a frequency. It all depends on the step edges. If it is, you're stepping up to a current where you get multiple spikes, then in fact, you would always get roughly the same frequency every time you spike to that current or you jump to that current and
All right.
stay there. And for the duration you stay there, you would get that spike continuing. Spike oscillation continuing.
Because of the bistability near that threshold.
Correct. Yeah, because it really turns out what determines whether you continue to repetitively spike or not. You can kind of see it off this curve here. It's a question of how it, you might go, well, maybe it has to do with all these dynamics here. It's like, no, it has nothing to do with that for the most part. It has almost everything to do with how fast is this transition right here in the recovery. Because if this transition is fast enough, then that becomes a fast enough transition that then goes through the destabilization of the sodium channel, and then that causes it to fire. And so what causes this slope is actually the input current in terms of recovering out of the hyperpolarization and pulling you up. So that's absolutely the key thing that actually sets you from the one side to the other, that sets you from repetitive firing to single spike and stop.
Yeah, there's been we have to probably wrap it up, but there's interesting work on annihilation where you're already spiking, and you can actually, if you're during the certain phase of the spike, you can give a little pulse. It can knock out the spiking. In fact, you can even give a little hyperpolarization and it would knock out, or even a depolarization at a certain phase, it can knock out the spiking and go back to steady state.
Absolutely true. Absolutely true. And we've seen
experimentally in actual nerves that's been
Yep. We've seen the same things as well. And there's good reasons for that.
Yeah, it probably has a similar bifurcation diagram. That's what we're talking about now.
Yeah, the core physics. Yeah, the core physics are very similar. But what was really neat about this is that it got all the physics kind of to match all the way through this.
The one thing you can't do with the circuit is run the circuit backwards, or you can't see unstable solutions.
You come down to a point, back to a point.
You can't see it.
Yeah.
You won't be able to see it because it's also a higher, even the model, it was higher than 2 dimensions.
I mean,
so
you can always do, I mean, you can always like play with the nonlinearities in such a way to sort of invert the stability, but that's probably...
You can't do that for a system higher than 2 variables. Only a 2 variable system can you reverse it.
Yeah, it's an interesting call. I have to think about that a little bit.
And so, so that's the problem with just doing it by circuits, is that there's a lot of things you can't see.
There's some things you can't see, although there's some things you can
see from mathematically. You can see these things.
Right. There's certain mathematical techniques may or may not always be accessible, but a lot of them are. So.
Yeah, but you have to have equations first. So going from this to an equation, that's beautiful because then you can test lots of things with the actual circuit.
Yeah, and so all of these things are there. The couple of the comments that I would have thrown out here as well is that there's a whole bunch in higher level conversations of computation and what that means. The other question then is how you actually make this Hodgkin-Huxley structure in an FPA. And there's a whole bunch of questions of how you translate these ideas into the FPA circuit. Remember I mentioned that, this is sort of the classical formulation. Well, in FPAs, it might make more sense to make this bandpass filter in a different way, which gives me relatively similar dynamics, but worth discussing. And there's things that you do that are native to that structure, which is, by the way, where when I showed you the picture of the simulation or the experimental stuff from before, that's kind of where that would have come from. And these spikes are, this is actually things that you can pick up from the experimental model directly. And we can talk about details of these spikes, and I'm sure someone would look at these spikes and go, but these spikes feel differently than